All right, finally, we're ready to talk forces and moments for rigid bodies. And these equations will start out familiar, but they get a little bit different. So we're going to start out by talking about our sum of the forces on an object. Any rigid, and these are still rigid bodies, so the sum of the forces on the rigid body is going to be the rate of change of the linear momentum, which, since the mass isn't changing, only the velocity is changing, we're going to get our ma. Linear momentum is a vector, and acceleration is a vector, so just the sum of the forces equals ma in 3 dimensions, so that's comforting, that's the same. And remember, this is the acceleration of the center of mass, so you've got to have this bar here. And whenever you're using this equation, the same as with normal, you still want to be drawing a free body diagram to show which forces that you're remembering to put in there to make sure you haven't forgotten any. All right, and now we're also going to be talking about the sum of the moments. Now, the sum of the moments is going to be equal to the rate of change of our angular momentum, which means we're going to be taking the derivative of this I matrix times this omega vector. Now, we want to be careful about how we take this derivative because this whole thing is rotating. And so we want to be thinking it's more convenient for us to think about this all in a rotating coordinate frame. So let's say you have your object here, here's an object, and it's rotating. You don't want to be redefining this matrix for every little rotation it makes, right? We want to be defining this matrix in a coordinate frame that's rotating with the body. So that's why we're going to take the derivative of this part, but then we're also going to take derivative of how it rotates, which means that we're going to have our I matrix, which is going to be constant, times now the rate of change of this omega within that rotating frame is going to be an omega dot, or as we've been calling it, the angular acceleration or alpha vector. And now we're also going to have the rotation effect, which is however that coordinate system is rotating, crossed with the vector that you get when you multiply this I matrix times the omega vector. And that is going to equal the sum of the moments. And now remember, there's going to be 2 points where this is going to be good to take the sum of the moments. So remember to sum the moments about either the center of mass, or you can sum the moments about some fixed point O. And then this equation holds. All right, now when we actually go to use this, you're not usually going to use this form. We're going to talk about 3 main simplifications, sort of special cases that will cover most of the problems you'll solve, and all of the problems you'll solve in this class. So there's 3 special cases. And the first one is called principal axis rotation. The second one is called parallel plane motion. And the third one is all about our gyroscopes. Or actually, I should be a little bit broader because it doesn't always say it's a gyroscope, but gyroscopic motion. Gyroscopic motion. Now, let's think about, and these are simplifications for how we're going to use our sum of the moments equals I alpha plus big omega cross I little omega. Now, the first one, principal axis rotation, is for any I matrix that's going to be assigned to a specific orientation of your body. And for any body, there exists a specific rotation for which the I matrix is diagonal. So, and that specific orientation is called the principal axes. So think about for something simple like a cube, the principal axes are going to go right through the center and perpendicular to each face. So for principal axis rotation, we have I is going to be equal to I x x 0 0 0 I y y 0 0 0 I z z. Right? So our I matrix gets very much simplified because we don't have any off diagonal terms. And so you should, if you see sort of a symmetric object, you should know that that's going to be principal axis rotation. And I have some other examples of symmetric objects. So you only need two axes of symmetry for this to be true, because in this case, like if this is the z, then because it's symmetric about the x and the y, then all those off-diagonal terms are still 0. So this would be a good shape for a principal axis problem. Books are nice and symmetric. Dynamics. So they're going to be good problems for principal axis rotation. Various pens, if you neglect the little clip part. Other objects, here's a glass. So all of those objects are going to be good for principal axis rotation. And even objects like this object that maybe doesn't have a lot of symmetry going on for him, then there still does exist a principal axis rotation for the I matrix for even a strange and irregular object, but you might not know what it is. So maybe that won't be a good principal axis rotation problem. But this is one type of simplification where we simplify the I matrix. All right, now what is parallel plane motion? So in parallel plane motion, we're going to simplify the little omega vector. So in that case, this is only in one direction. So here we have our omega vector here and our alpha vector as well, right? Our alpha is also going to be 0, 0, and AZ. So the only rotation is happening about one axis. And we'll go into why that's called parallel plane motion, but I guess if you picture it, right, and you have this like strange object here rotating about this axis, every point on this object will move in one plane. And so if every, and each plane will be parallel to all the other planes of motion for each point of mass on the object. And if that's the case, and or if you can put your omega vector in a form like this, where it's only one axis, then you have parallel plane motion. And now finally, gyroscopic motion. Gyroscopic motion is the most fun, but it's a little bit almost harder to think about. But we are talking about gyroscopic motion when we have some omega vector that is in one direction. Well, that we have some spin velocity. That's the way to think about this. Is that omega, little omega, is not equal to big omega. But in fact, that we have our little omega is going to equal some spin velocity. And this is going to be much bigger than this. So we're going to have some spin that's happening about symmetric axes. And so then we can approximate our angular momentum as IZZ times our spin rate. And we're going to assume that that's constant usually for most gyroscope problems. And so then this term represents that the change in the momentum is going to be mostly due to the rotation of this large angular momentum component in the z direction. All right, so these are the three different types of problems that we're going to use. And we have on your formula sheet for the first type of problem, principal axis rotation, these are going to be Euler's equations. And here they are at the bottom. We'll prove them next. And then for parallel plane motion, we've got some parallel plane motion equations here on the formula sheet. And then for gyroscope, we can talk about two cases, a simple gyro and steady precession. Right, and that's going to take us through the end of chapter 7.